This is a session for electrical model building toolset. And in this session, we will mainly discuss of how to use the tools that were developed at BBP, in part for the human brain project that are BluePyOpt, BluePyFE, and EFL. All of that with the purpose of creating biologically realistic electrical neuron models. So here is how it's going to go. So it will be mainly divided mostly divided in 4 parts. I'm not sure exactly how much time we will spend on the different parts, but it is unlikely that the full tutorial will last for the 3 hours that is indicated on the program. So feel free to let me know when you feel like you've got enough, you got what you were interested in, or if you are also curious about something else that is not part of the slide of the curriculum, that's perfectly fine as well. So during the first part, I will just give a general overview of, let's say, the principle of what it means to build an electrical model, especially a realistic electrical model. And then we will go through a first tutorial that will briefly, we apply this principle on a very simple cell that's just made of a soma that contains a potassium and a sodium channel, and we'll try to find its parameter to match the spiking frequency of some EFIS data, of some electrophysiological data. And then we'll go back to the theory and we'll go a bit further in all of this principle. And then again, we'll go back to the tutorial and do something a little bit more detailed. So don't hesitate to stop me at any point if you don't understand anything. We are not that many people in the session. So if you have personal questions about your project, about how you could apply a specific technique or a specific method to your research, don't hesitate and go for it. I just lost my presentator notes. Okay, I have them. So at the first, maybe if some of you could tell me what's their background, because I don't know the names of the people who are here. So I just wanted to know if you already know what is, if you already, for example, built or used point neuron models, if you have already built or used detailed neuron models, and if you are rather like engineers or software developer or scientists. I'm not sure if some of you are motivated and would like just to tell me what they are doing. I would take that nobody is really motivated to talk right now. And so just a disclaimer is that I am not a neuroscientist, so I'm a software engineer, and originally I'm a physicist actually. So if I say something a bit too hand-wavy about neuroscience, don't hesitate to correct me. I won't be offended. So I'm really a software engineer and a research engineer. So the first part. So in this part, as I say, I will present for those who are not familiar with it, what it means to build an electrical model and how it can be done using the software developed at the Human Brain Project. So the first question is, what is biologically detailed electrical neuron models? Because when we hear about neuron model, we can all think about very different things depending on what is our background. And so here, when we say a biologically detailed electrical model, we oppose it to a point neuron model. So point neuron model can be artificial neural network. It can be leaky, like here, leaky integrated and fire models. But here we are talking about this neuron you can see in the middle that's composed of a morphology, so a 3D reconstruction of a morphology, plus a set of equations, a set of what we call ion channels, or sometimes we could even call them mod file neurons, that contain set of equations that are parameterized and that define the electrical behavior of the different section of your model. And so when we say that the model is electrical, we mean that because it has an electrical activity, that means that this model aims at reproducing the activity of a real neuron. So it's a model that can be stimulated either at the soma or in its dendrite or even in the axon. And it's a neuron that will produce a voltage response as a result to this current stimuli. And so this neuron might be able to integrate input from the dendrites, might be able to generate an action potential at the soma and propagate it along its axon and so on, and even be integrated after that in a full circuit of many neurons. But I won't talk about that today. So, and we're going to do so. So we're going to build this electrically detailed model using open source software and in Python. So what we're going to integrate today, so it's Python, of course. I hope most of you know how to code in Python. There is nothing too complicated in what we are going to do, but if there are any issues with the tutorial, just let me know. And in Python, we are going to use 3 open source software that were developed at the bluebrain project. So EFL, that's a library used to extract electrical features from electrophysiological recordings, be it experimental electrophysiological recordings or recordings generated by a model. We will use BluePyEFI, which wraps this EFL package to extract on many traces, and we will use BluePyOpt, which is an optimization package that we will use to optimize the parameter of the models. And of course, to run the models, we need a simulator. And yesterday during the presentation, you might have seen Nest, or I think there was Arbor as well that was presented. But today we will stay on a very familiar simulator that is Neuron. So although today's session, this morning, won't be about the simulator neuron itself, if you want to learn more about neuron or core neuron, there is a session this afternoon, I think, also by someone from the bluebrain project. So as I said, the goal is to go from biological data obtained from experiments to a functional neuron electrical model that we can run in the simulator. So here, neuron. So what do I mean by experimental data? They can have many, many different forms of experimental data. Here, we will mainly consider first 3D morphology reconstruction. So it means that we got sliced, and in these slices, we got morphology data. And this morphology, this neuron was reconstructed. So it's the process of creating digital reconstruction of the entirety of the neuron. And this neuron can reconstruct, can contain the axon, the dendrite, the soma, and all of the neuron is reconstructed in 3D. And then we get this point as a 3D file and can import it in the simulator. And the second thing we will need to build an electrical model is here electrophysiological data. And we will mainly focus on here whole cell patch clamp somatic recording data. So it means we are going to focus on sets of current stimuli and voltage recordings. But of course, if you had other type of electrophysiological data to constrain your models, you could also consider them. For example, you can get single data point from the literature. If an article say layer 5 pyramidal neuron fire at around 30 Hertz, then that can be used as a target as well for, let's say, an optimization process, or at least for you to know what you want your model to look like. But you can also get local field potential data. You can get pair recording data and so on. And finally, the third thing we need to build the model is, of course, a simulator. So that is the engine that is able to compute the dynamic of the model. And so to do so, we'll just need to fire up Neuron to load our morphology. And then there is a big step that will actually occupy a lot of the time it takes to build a realistic neural model, which is to choose the set of equations that will describe the dynamic of the model. So all the ionic dynamic, but can be also the calcium dynamic or other kind of dynamic you would like that would take place in your model. And we need to put, of course, these mechanisms where they're supposed to be in the neuron, and that's also sometimes a big question. So here, if you have if you really want a realistic model, there is usually a big bibliography work to do to know where the channel go, what kind of density they have, and so on. So here, websites such as ModelDB can help you to obtain this channel, to obtain this set of equations. Okay. So when we say we want a model that behave like the electrophysiological data does, or behave like a biological neuron, what do we mean exactly? Most of the time, we mean a model that have an electrical activity similar to the one of the biological neuron when subjective to the same current stimuli. So here you can see if we impose this set of three current stimuli that are presented on the left. So you have one step with a hyperpolarized step before and after. You have this long depolarized step with an additional depolarized step on top. You have a ramp stimulus and so on. And here you see experimental data. What we would like ideally, it's a model. Here it's a real model that we use at the bluebrain project that could reproduce some of the feature that we see in this data. But it's not enough to say that we want a model that behaves like the electrophysiological data. We actually would like a way to put this likeness into a scalar, into a number. So since we are doing computer science, we need one or many scalar to represent how good our model is. So one option would be to say, I want a model that reproduces the same trace as the experimental neuron. And you could define the fitness of the model, so how good the model is, using the mean square error between the experimental voltage and the model voltage. So of course that can work, but it is not the best solution, because let's say our model produces 10 spikes and the experimental data has 9 spikes. Then would you say that the model is bad? Well, probably not. It's just one spike difference, almost the same firing frequency. But if you compute the mean square error on these two traces, you will see a huge difference because the spikes will not align. And so it will result in a score that is meaningless. So we need another method to judge how fit is a model. And the result we use most of the time is to say that instead of aiming for voltage time series as a target, we could aim for features of these time series. So for example, if a model shows the same spiking frequency and action potential height as the biological cell, it would be a good model. And then we can just compute how good a model is by computing the difference between the feature, the experimental feature, and the model's feature on the same trace for the same stimuli. So that's what we're going to do. So here you can see there is a set, I put a set of electrical features that we commonly use. So you can see that there are some such as the action potential width, you have the action potential height, the speed at which the action potential is initiated and falls. You have the interspike interval, whichever one you would like to optimize for. You can also have the mean spiking frequency, of course, the adaptation index. So how, if your neuron is adaptative or non-adaptative, well, you can also try to put that into a specific feature. You can have information about the after hyperpolarization, how far it is from the peak, how deep it is, and so on. And so the goal is really to try to transform your voltage time series into a set of features that fully characterize it and that you can use as target for optimization without relying on the time series itself. And once you compute all of these, as the formula in the bottom left corner, you can simply compute the score as the absolute difference between the feature of the experimental neuron and the feature of the model. I lost my notes again. Okay. So now what we need to define features and extract them from the voltage traces, we need to define function, to define the set of function that can create this set of e-feature. And luckily for us, this was already done. And that is by the two first Python packages I will talk about today. So there is EFL, which is the electrophysiology feature extraction library, and there is BluePyFE, which is the bluebrain Python e-feature extraction library. So both of these have very similar name, is because they have very similar function. The first one only takes as input one voltage trace and returns an output a set of features, the one that we asked for. And this second package, BluePyFE, I will go a bit more detail about it in the second part. It's mostly used when you have many different biological cells and you would like to combine the features coming from all of these cells in a meaningful way. So I also added the GitHub link to these two packages if you are interested. So then once we have a model, it runs in a simulator. We chose the equation that we want to govern our model. And we have our feature, so we know what we are aiming for. But still leaves us with a question is how do we build the model? How do we parameterize it? How do we parameterize this set of equations such that the model behaves like our features? And how do we do we minimize this curve, this difference between the experimental feature and the model's feature? So the first trivial method, of course, is to do it by hand. So which can work in some cases. Let's say you have one or two parameters. It can be perfectly fine to do a grid search, for example. So as you can see on this graph that represents the score versus the parameter, on this simple of a fitness landscape, it can be very, very easy to find this optimal point here. But then it becomes a bit more complicated when most of the time we have many channels and we have many parameters. The fitness landscape can look extremely complicated. It can have cliffs, it can have bumps and mountains and many valleys. And in this case, it's very complicated to do a grid search simply because of the computational cost. We can take several hundreds of years. So this is not what we are going to do because it's not convenient. What we need here is an optimization method, such as evolutionary strategies or gradient descent and so on. And this is where the last of the three Python packages that we will use today appears. And this one is bluebrain, which is the bluebrain Python optimization library. So if you were to read the documentation of the bluebrain, it says it is an extensible framework for data-driven model parameter optimization that wraps and standardizes several existing open source tools. It simplifies the task of creating and sharing this optimization and the associated techniques and knowledge. This is achieved by abstracting the optimization and evaluation tasks into various reusable and flexible discrete elements according to established best practice. So in brief, bluebrain is the Python package that contains on one side the ability to build model in the neuron simulator, and on the other side, the ability to tune the parameters of these models in order to reach whichever target you want, most of the time electrical features. And so how does bluebrain perform this optimization? Well, it uses evolutionary strategies. And so right now we have two implemented. So for those of you who are not familiar with evolutionary strategies, so they are optimization technique where you start from a random population of an individual. Here, individuals are composed of the set of parameters that parameterize your equation, and iterating through an evolutionary process, so through generation, by selecting the best individual to the most fit individual of the previous population, we will try to mutate and mate the best solution to little by little converge toward the best set of parameters that makes our model behave in the way we want. So as I was saying, in bluebrain, there are two right now evolutionary strategies that are implemented. The first one is called IBEA. It stands for indicator-based evolutionary algorithm. So this one is the one that looks the most like a biological evolution. So you as I described, you get this set of solutions. You evaluate them to see how well they perform. You select the best one. You make them breed, and you get new generation, and so on. Unfortunately, this strategy has some drawback. Is that as the mutation and mating is purely random, sometimes you can end up jumping around good solution while never actually reaching them. And to actually reach the best of the best solution, you need a huge number of generation, and you have to hope that by chance you will jump on the best generation. So of course, since this method was invented in the 90s, there have been many improvements. And a very powerful method that is still very used today is the covariance matrix adaptation. So this method is a bit more abstract. It doesn't really follow any biological evolution. You can imagine that you have a kernel that represents the covariance of the fitness landscape of your problem. And this covariance matrix will try to fit some value in your fitness landscape, and then we'll try to converge little by little to the bottom of the valley. So it's a bit more like a gradient descent, but as if gradient descent has many individuals in the population that were evaluated at the same time. So it made use of parallelization. And that would together try to find the best spot and the best shape to evolve in this fitness landscape. And this is the one we'll use today because it's way less compute intensive as well. So to summarize this part one, so we have these little steps. So first we start with voltage recordings, which are here wholesale punch clamp recordings. For these voltage recordings, we are going to extract some E features. So we're going to end up with a set of electrical features, and that will be done in EFEL and BluePy FE. Then with this set of electrical features, plus a set of equations, so a set of ionic mechanisms, plus a morphology, so a 3D reconstruction, we will take all of that and instantiate a neural model in BluePy. And in BluePy will take place an optimization process where we will iteratively apply the evolution strategy, so generate new models. We will compute the traces generated by these models. And on these traces, we'll compute the E features and the scores, and then apply the evolutionary strategy again and slowly converge toward good solutions. And from all of that, will come an electrical model. So as you can see here, there is a start of an arrow that I cut, because then the rest of this drawing concern model building, but we will not talk about today. So I propose that we start here with the first hands-on. So there are two ways we can do this. Either you just want to look at what I'm doing, or you want to follow along on your own computer to try things on your own. So I recommend that you do so, but you also try to use the software as I do. You will probably learn much more than just by watching me do it. And I also recommend it, especially if you already have Python that is set up on your machine. Although I also put all of the things you might need for a tutorial on the Colab. So I will give you, this is the link of the Colab. I will show it to you. So either if you already have Python, you can git clone this repository, bluebrain simulation tutorials. And there is a folder called ebrain 2022, and that you can do it in local. Or you go to this link, and here you will have exactly the same data, exactly the same notebooks, and you can do it purely on the cloud. So I'm not sure if, are there people who want to do the hands-on at the same time as I will do it?
Can you please just copy the link into the chat?
Absolutely.
Thank you.
You would like the eBrains? Okay, this one.
Yeah, that would be great.
Alors, here you go.
Yeah, thank you. Good morning. I'm gonna try to do it at the same time as you do.
Okay, perfect. So are there other people who are going to do it in local and who would like some time to set up? Because you might need to install Git if you don't have it, and to take time to clone the repo. So yeah, let me know if you need some time to do so before I start talking about the notebooks.
Yeah, maybe let's give the people 2 or 3 minutes.
Okay, let's do that.
So then they can try
Then
to
I will
install everything, and we start again at 9:28.
That's perfect. This way I have time to go get a coffee and some water, and I come back.
Would be great.
Perfect. Thanks.
Okay, let's start again.
Okay. Opening Drive. So once you are on the collapse, for those who have chosen the collapse option, you can, sorry, maybe if go back to you can click on Drive. And here go to Open in Drive, and it should open this this window. And here, oh, sorry, that's not what I want. I remember there is a link to open the lab is here. Sorry, my bad. You have to go to Lab and click on Open in Lab. It's not Open in Drive. And here you can choose which lab execution site you want. I would just stay on the CS because it's the one I'm usually working on. We can select it, and it should open a Jupyter Lab session. And in this Jupyter Lab session, we will go to tutorial 1, and we will open the Simple Cell notebook. Is that okay for everybody? I will take that as a yes. And
yes,
so,
thank you.
Perfect. And so here, in this first notebook, we'll try to extract electrical features and plot some traces that I put in next to this. In EFEs, we have a set of 4 cells, 4 experimental cells from the mouse that contains a lot of data. And we'll try to open some of these and to see what kind of electrical features we can extract from them, and then see if we can create a very simple model that has the same behavior as this data. So the first thing we'll do is to install BluePy EFE and BluePy opt, which will automatically install EFL in the background, and then we will import what we need for the plotting. So let's do that. And for those who, for those who want to do it in local, you will have a script called create venv that will create a virtual environment and install these packages as well. And then you can open your own Jupyter session and open the notebook as well. Okay, so maybe let's go to the documentation of BluePy EFE 2 and see a bit what BluePy EFE 2 is about. Maybe some of you already used BluePy EFE in the past, but we had a big version change this week. So now we have the whole the very like lots of new stuff. So maybe you will need to become familiar again with the package. So BluePy EFE aims at easing the process of reading experimental recordings and extracting batches of electrical features from these recordings. To do so, it combines trace reading functions and features extraction functions from the EFL library. BluePy EFE outputs protocols and features file in the format used by BluePy opt for neuron electrical model building. Okay, so that's great because it's what we want to do. So one of the low-level class in BluePy EFE is called simply cell. It is empty at the start, but will become the recipient for the recordings data associated to the cell. So as I saw in the subdirectory EFEs, we have some data. And so I chose one of them at random, and we'll simply instantiate a cell object for it. So this is done by just passing the name we want to give to the cell constructor. And then to read a data file that matches this cell, we simply need to provide the metadata associated to the file in the form of a directory. So here, for this specific is IBW format, we need to provide the file to the current, the file to the voltage, and then the units for these two files. Here I'm also passing the sampling rate, although you could read it from the header of the file. And this is something I will talk about later. We are also passing the liquid junction potential correction. For those of you who don't know what is liquid junction potential correction, it's not very important right now. I will talk about it later. So we're going to instantiate this dictionary. And so, okay, that's all good. This is for you if you want to do the notebook later. I left these notes so you can also go through the notebook. Once again, you don't need my voice to guide you. And now we are going to use this metadata so to to read the data file. And this will, so here, cell.read recordings, we pass our files metadata. We give a name to this protocol. Here we'll call it ID REST. So ID REST is just a naming scheme that we use at the bluebrain project to call a simple step current. So we call it ID REST because you can see the file is called ID REST. And then we can print this this recording that was read. So we can see the amplitude of the step was 1.1 nanoamp. We don't, so here amprel, I will talk about it later. We have some config, so about the file metadata we pass to the cell. We have a current array. We have like many metadata about this recording. And one of the ability of BluePyFE is to plot this recording. So we can grab this recording, that is the recording 0 of the cell, and we can plot it. Oops, sorry, I need to do some. Not sure why it. Nope. I will just, how do I? It really doesn't want me to push. Does anyone remember the command to change the Jupyter Notebook mode to plot inline? I think it's something like matplotlib inline or Jupyter Notebook inline. Stack Overflow always has a solution. Matplotlib inline was correct. Oh, I didn't put the right. Perfect. Okay, so I didn't have the right. Put an exclamation mark here. Okay, so and here we can see our trace. So on the top we can see the current stimuli. So we can say that it was a square stimuli that lasted for 300 milliseconds, and that had an amplitude of 1.1 nanoamp. So we can, it's indeed 1.1 approximately. So we can see that this trace has actually two things on it. It has one of blue trace, which is the one that was recorded by the experimentalist. And we also see a dashed orange one. And this is actually the step that was detected by BluePyFE. So when BluePyFE saw that we entered the trace as an ID REST trace, he was like, oh, I know ID REST. ID REST is a step. And it tried to detect the step. And so that's how he guessed which was the amplitude of the step. So as you can see, this current recording is noisy because every time there was a spike in the voltage recording, there was also some artifacts in the current recording. And so here at the bottom, we see the voltage in millivolt, of course, versus the time. And so we can see a burst at the beginning, then we have a train of spikes, and then when the current stimulus stops, well, the spikes stop as well. So what we would like, of course, from our model is to have this behavior. So if we send the same stimuli to our model, we want the same voltage response. Okay, this I will skip. Okay, now let's go to the features. So we say that we don't want our model to be evaluated based on this specific voltage series, but instead on the set of features that will be extracted from this voltage series. And this will be done in EFL. So maybe we can go to EFL, and I will also open the doc of EFL. So EFL is a slightly older package. I think it was written in maybe 2009 started, something like that. So the EFL library allows neuroscientists to automatically extract features from time series data recorded from neuron, both in vitro and in silico. Examples are the action potential width and amplitude in voltage traces recording during whole cell patch clamp experiments. Okay, so yeah, this is interesting. The core of the library is written in C++, and the Python wrapper is included. So at the moment, we provide a way to automatically compile and install the library as a Python module. So that's great. That's good for us. And then we can have a look a bit. So here you can find again the figures I use for the slides. So it's just a general presentation of all of the features that exist in EFL. And you also have a pseudocode description of this feature. So here, time to first spike is simply the difference between the time of the peak and the start of the stimuli. Time to second spike is the same to the second peak time, and you do the difference with the stim start and so on. So here are about time intervals. Then we have features here, maybe about some amplitude. You see action potential amplitude, AP amplitude for the first AP, amplitude for the second AP, for the last AP, and so on. So we have many features that we can use in the EFL package. So here I selected a few. I call them interesting features. There is spike count, the mean frequency. So spike count is simply the number of spikes in the spike train. Mean frequency. So this is the frequency of spiking, but only between the first and the last spike of in the spike train. So let's say that if if the cell only started to spike here, this would not be taken into account to compute the mean frequency. It would only be in this portion of the signal. Then I chose the ISICV. So ISICV stands for interspike interval covariance. So it's just how much variation there is in the interspike interval. So if you have a very regularly spiking cell, this value will be extremely low. And if you have an irregular bursting cell or stuttering cell, then this value should be quite high. Then I also put the amplitude of the first AP and the width of the AP. So now that we have this list of interesting features, we can do cell.extract features. We pass the protocol name for which we want to extract this feature. So here it's ID rest, and we pass our list of features. And after that, we can print for our cell for the first recording the features that were computed. So we see that we get an AP amplitude of 107. So of course that's relative to the voltage base. It's not an absolute number. We get the AP width that is 2.8 milliseconds. We get the ISICV that is quite low, 0.05. We have 34 spikes, and we have a mean frequency, so a mean spiking of 17.2. Okay. So now we can go to a second step, which is to create a model that can reproduce these features. So we already had a look at BluePyOpt, so I'm not going to go over it again. And so the first thing we will do to create a cell model that can reproduce these features is to create a template. So re-instantiate the model in Neuron. So as I said in the presentation before, the template will consist of three things. So a morphology, a 3D reconstruction that I put here in the simple.swc. And here this actually is extremely simple because it's actually the morphology is composed of only 3 points. So it's going to be a small cylinder, so a small soma as a cylinder as a soma. And this cylinder has a diameter of 10 micrometer both in radius and in height. Then we have mechanisms. So these are the set of equations that will govern our models. And for this model, we have two. We have this NATG mod file and this SKV 3.1 mod file. So NATG is a transient sodium channel, and SKV 3.1 is a potassium channel. So here I won't go into the detail into this file. You can find them on ModelDB if you need some to build your model, but you can see that you have the equation that are governing the opening and closing of this channel. And finally, we can see that these two channels have parameters. So here we can see that there is GNATG bar, so the maximum conductance for this channel, and here GSKV 3.1 bar, so the maximum conductance for this SKV channel. And so these are the parameters we'll try to optimize. So we will import BluePyOpt, and we will load first our morphology. So as it's written, by default, a neuron morphology has a soma, axon, apical down right, and basal down right. In our case, that won't be the case. We'll only have a simple soma, and we'll first start to instantiate a location at this soma. So this will be useful in the future because we will say, I want to stimulus at this place, or I want to put a mechanism at this place in the neuron, and this place will be the location of the soma. And I will also instantiate a location that is everywhere. So I will say, when I point to there, you put it everywhere on the neuron. And once we have that, we can we can instantiate our mechanisms, so our mod file, and put them where we want in the neuron. So I will loop over our two mechanisms. I will give them a name. So for example, natg.somatic with the suffix natg, and the location will be the soma because we only have the soma. And then here for a bit of change, I will put the mechanism that we didn't talk about because it's intrinsic in the neuron simulator, which is the passive channel, and this passive will be, I will put it everywhere in the model. So once we have that, we can define the parameters of the model. So the parameters we saw there, but there are also parameters that are global to neuron or that already exist into neuron. So for example, we can define the capacitance of the model, which is an intrinsic property of the model. So the capacitance will be called Cm. So we'll create a Cm param, which has the name Cm. So we're going to give it some bounds. So the bounds will limit how much this parameter can vary if we search for it either by hand or an optimizer. So here it means we'll force the optimizer, or we'll force ourselves to stay between 0.5 and 20 for the value of the capacitance. And the location, we'll put it at the soma, and this parameter is not frozen because as it has bounds, it means we can vary it to trying to find the best value to get the best response from the model. And then we can also create parameter that represents the maximal conductance of the sodium and potassium channel. So the first one will cause a GSKV 3.1 bar, and it's associated to the SKV 3.1 channel, and it's at the soma. For this one, we'll put bounds of 0.01 to 20, and this parameter is still not frozen. Here it's a bit of maybe you shouldn't have done that, but it's just to illustrate that the parameter can also have what we call scalars, so they can be distributed in a nonlinear way, for example, along a given section. Let's say you were building a model that have dendrites. You could say, I want my channel to be less present close to the soma and very present at the tip of the dendrites. And this kind of scalar allows you to do that. Then we can create a second parameter, the same for the second mechanism. So here GNATG bar for the NATG channel, somatic still, and with bounds here 0.01 to 15. Still, we are at the soma lock. The parameter is not frozen, and we have a linear scalar. So here the parameter will be the same along the whole section. Okay, I'm not sure if I executed this. Let's do it again. And finally, we will add some parameter that represent the reversal potential and the passive current for the potassium and sodium channel, and then some leak as well. So leak conductance and leak reversal potential. So here we'll choose 10 to the minus 4, minus 62 millivolt for the passive reversal potential, 50 millivolt for EN is 50, or 50, and minus 90 for the EK. Okay. And finally, once we have all of that, we can instantiate in BluePy a cell object. So this is not the same cell object as the one we had in BluePy IFI. If we go back to the start, we had a cell object here. Here it's a cell object that comes from BluePy IFI. Now we have a cell object that comes from BluePy opt, and this time it will allow us to instantiate something in the neuron simulator. So we instantiate this cell object by giving it a name. So we took the name of the IFI cell that I have from the start. We pass it our morphology, our mechanisms, all our parameters. And now we should have a cell model. So yes, we has the right name. We have our simple.swc, our mechanisms, passive, our parameters. Some are fixed, some are not fixed. So everything is good. So now that we have this model, And the second thing we need is what we call an evaluator. So the evaluator will be in charge of running some protocol, some set of stimuli on the cell, and to see how, and to perform the computation for the fitness. So to say, based on these recordings, I get this value for the E features, and thus the fitness for this model is that number. So same again, I will define a somatic location, so location at the soma, to say, please put the stimulus at the soma. And then we'll create this stimulus. So here we'll give it the same name as we had in our IFIS data. We'll call it ID rest. And we'll say that it's a square pulse. And this square pulse has some parameter, an amplitude, a delay, duration, a location, and a total duration. So the duration is the duration of the step, and the total duration is the duration of the full recording. And of course, we'll take this value from the IFIS recording. So in our IFIS recording, we had it has an attribute called hype amp, which is the hyperpolarized amplitude. So it's the holding of the cell during the patch clamp experiments, and we pass that as amplitude. Here, for this holding current, we'll put a delay of 0. We want it to last from the start of the stimulus to the end of the stimulus. We'll give it a duration, therefore, that is the end of the recording, and total duration, that is also the end of the recording. And on top of that, we'll put a second square pulse, that is here the step. So first we established the holding, and then on top of that, we put the step. So here the step recording, and this time it only onset of the step and ends at the offset of the step. So we take these two from our IFIS recording as well. And we're still at the soma, so everything is good. And the last thing we need to set up this protocol is to define a recording, so a fake voltage patch clamp in our neuron model. So here it's called a comp recording, and we put it at the soma, and we want to record the voltage, so the variable V. And once we have both the stimulus and the recording, we can instantiate a protocol. Okay. And then we have this protocol, so we can run this protocol on our cell model. So the first thing that's needed right now is to compile the mechanisms. So we have these mod files, but Neuron by default does not know how to use these mod files. They need to be compiled. And so there is this Neuron command that you might learn more about this afternoon if you go to the Neuron session. So Neuron IV mold mechanisms. And when you run this command, it will create this folder that should contain your compiled mechanisms. You might get many more lines that I did here. So once we have our mechanisms, we can instantiate a neuron simulator still through BluePyot. And finally, we can choose by hand a set of parameters. So here we only have to specify the parameter that we set as not frozen. And we'll say that for the potassium channel, we want a maximum conductance of 0.1. For the sodium, we want also a maximum conductance of 0.1, and we want a capacitance of 4.5. We will pass this set of parameters we chose by hand to the model. We'll pass our cell model, we'll pass our simulator, and we'll run all of that and get a response, a set of response, which is a single one. And we can plot it. Okay, and we get something. So indeed, it starts and ends at the same with the same timing I did our experimental data, but we can see that our spiking is completely off. So we get this very strange burst at the start with a decreasing amplitude of the APs. Maybe we can see it a bit more clearly. We restrict it. Okay, so we can see this very weird oscillation, which kind of look like AP, but it's not. It's definitely not what our experimental data was about. So now the second step is to optimize the parameters of our model for it to reproduce the data we have. So to do so, we will need to perform it automatically. We don't want every time to have to look at the trace and say, oh, this does not look like our model. So we want to set up a way in the evaluator to automatically compute how good this trace is. So to do so, we are going to define if-else features. So we are going to tell our evaluator, I want to compute this feature on my trace. This is what I expect from this feature. So what we saw experimentally, I want the same spike count, the same AP amplitude, and so on. And so please use that to compute how good the model is. So what we'll do is that we'll iterate over the interesting features we use to extract the features from the experimental data. We will check in our experimental recordings if this feature is present, and if it is present, we will instantiate a BluePyOpt object that has the same value as target, the same value as the experimental recordings. And here, I will talk about that in the second part. We'll also define a standard deviation, so an error bar, if you prefer, for the target we are aiming at. There are other parameters, such as from which millisecond so when does the stimulus start and end? It can be during the step, but it can also be before the step or after the step. Here we put it during the step, because we have, for example, features such as spike count that only exist during the step. And we also give it a name. So here the name will simply be the name of the feature. And finally, we need to specify for which recording we want to compute this feature. And here the recording name will be idraest.soma.voltage. So we can define this objective. So we have, it's good. We have one objective per features. And finally, we will pass this objective to a cell evaluator, which will contain the cell on which we want to run the protocols, the protocols we want to run on these cells, the features to compute on these protocols, and a list of parameters. So here's the parameter we defined above. And we also pass the simulator. This way you don't need every time to say protocol.run and then pass the simulator. So now we get a bigger object that's called a cell evaluator that contains the cell itself, but the fitness, the protocol. So here are two square pearls, one for the holding current and one for the step itself, plus a set of e-features that are all defined by a name, timings for which they are computed, an experimental mean, and some standard deviation. So this is our error bar. And finally, now it's much more simple. We can use this evaluator to compute. We are going to take the same default set of parameters that I defined here. So a bit of a random guess of what the parameter could be for our model. And for this set of parameters, we can compute the values of the e-features for the model. So we see that spike count 7, mean frequency 156. That's very large. We have an ISICV that's approximately the same at what we saw experimentally. AP amplitude, it didn't even work to compute. AP width is a bit small, 1.2 versus 2 that we had in the experimental data. And we can also ask for the scores. So the scores will be simply a value of how far we are from the experimental data. And this I will talk about it a bit more in the second part of theory. But what I can say right now is that when we want to evaluate our model to say how good is our model, we can simply define a fitness as the sum of the score. So what we want is to minimize this value. So we do like our fitness to be 0. And right now we have a fitness that's around 350. So what tells us something about our current model? It's good at 350. And now what we are going to do is to tune to find the best set of parameters to get this value, to minimize this value. So the easiest, the most trivial way to do so is simply to do it by hand. So if I take my sodium, potassium, and my CM parameter, I can iterate over them and do a write search. And every time evaluate this set of parameters and plot when we improve the fitness, see what we get as fitness for this set of parameters. So we see that iterating through this, we get actually better and better fitness. And we quickly find a solution that's already a bit better than what we did when we guessed by hand. So you can see fitness of 89. Yeah, it keeps going. We can have a better one, 87. So you can see this is quite clunky because we need to iterate through many sets of parameters when we do it through write search, even some that have absolutely no meaning. And it takes a lot of time because we need to do, if we increase our number of parameters and we increase in the cube or the square, the number of loop we need to achieve to iterate over all of these parameters for the grade search. So maybe we can stop it. I'm not sure if it's done. Not yet. Let's stop it. It's not really going anywhere. So we get a best parameter. For now, our best parameter has a fitness of 82.85. So we can, I copied it actually. I take it from there. We can see what it gives as a trace. Okay, so we get something. Let's see. 500, zoom a bit the onset of the, oops. Okay, so we get a spike train that is very dense in spike. Let's say it has very large spiking frequency, but it's already better than what we had with our initial guess. But as I wrote here, the issue with this process is that it's extremely slow and it's also a bit stupid. So we just iterate through everything and hope that we get a good solution. But of course, we have no way to reach a solution that would be in between the array, our grade, in between the points of our grade. So then the second method, that's the one used in BluePyOpt, is to use an optimizer. So here we'll try to run the optimizer for 10 generation, and we will put 10 individuals per generation. So every generation will have a set of 10 solutions. We'll select the best 5 one, mate and mutate, and go on like this for 10 generation. So from BluePyOpt, we will import the CMA optimizer. We will pass it our evaluator. We will select the single objective CMA optimizer. There is also a multi-objective one if you prefer to have more exploration, let's say, in your optimization. And we will say that we want 10 individuals per generation. And we'll run this optimizer for 10 generation. Okay, so that might take some time because here we actually need to do 100 evaluation. So for each generation, we need to evaluate 10 models. So it will run for some time. Here as well, you can see that the optimizer will create a checkpoint file, a CP file, checkpoint file, that contains the state of the optimization. So in case at one point you want to restart from a previous optimization, you can also say here, I think there is a command called resume or something like that, and pass this path, and it will resume from an existing checkpoint file. So it's done. And from this optimization, we got a final population. So the population during the last generation, we got a Hall of Fame that contains the best of the best during the 10 generation, which one was the best model. We got a log and we got a history. So what we will do is that now we will test our best model. So we'll take the best of the Hall of Fame, which is the first element of the Hall of Fame, and we will run the protocol on it and plot the response. Okay, and we get this. So we get fitness of 48, so way better than what we did by hand. Maybe we can zoom again. Sorry. Zoom again on the first spike on the onset of the stimulus. Okay, and we got something that's already quite nice. I mean, it really looks like real spike. We have an HP. We have this onset of the AP that looks nice. The HP is a bit deep compared to what we had experimentally, but of course we didn't put any feature about HP depth. So here the model could not optimize for that. So that's quite good. And we can also plot, we can also visualize how the fitness improve with the generation. Since we say we run for 10 generation, we can have a look at what was the average fitness for a generation and what was the best fitness at each generation. And here we get this. So the blue one on top is the average fitness, and the orange one at the bottom is the best fitness. So we could see that with the passing generation, our model got better and better. So here it's a log scale, so be careful. And of course, if we had continued running this process, maybe our model would have kept increasing. Okay, so did the people who went through the notebook at the same time I did arrive at the same point, or did you meet any issue?
Yes, I've arrived.
Perfect.
Even that I've arrived, I had an error on compiling the mod files of the neuron.
Okay,
But
what kind of error did you get?
that cannot, the permission was denied for the make mod 2C int. But in any case, it worked. I don't know why.
Okay, okay, so it's good. Perfect. If it works. If it works, it works.
Yes.
Okay, great. So
Thank
this
you.
was the first tutorial. Now I think we can have another 5-minute breaks. And after this second break, we will start again, where I will try to go a bit further in the theory of software. So we'll go back to slides. And then after that, we will have a second tutorial, but with a bit more advanced if processing and a bit more advanced model. So see you in maybe at 10:08. That's fine with everybody.
Yeah, would be fine.
Perfect. Thank you.
See you later.
While we wait a bit more, I will just try to improve a bit our model. So if we go back to our interesting features, let's go to feature description, fast AHP, AHP depth, the first after hyperpolarization. Let's take, for example, AHP time from peak. Maybe AHP depth. Okay. Let's run everything again. This one, stop. Take some time to run again. So this is a process you will see often when you create different models, is that you optimize something, you instantiate your model, you create your template, you optimize things. Then you go back to square one. So you go back to e-feature extraction, you define new features, you see what was not going well in your model, and you try to fix that and iterate. Let it run until the end, and then we can restart. Okay, so here what we see now that we added these two features, of course, our fitness is worse than before, which is expected because our fitness is computed as the sum of the features. So if we add features, of course, the fitness is going to increase. I don't see a big improvement in the shape of the AP. So, okay, so that's something. So maybe our model is too simple to be able to capture this kind of dynamic. So we need more complex mechanisms. Okay, so I think we can go back to the slides. Everybody still see my screen all right, I think. And my notes. Perfect. Okay, so now we can maybe go to the more nitty-gritty of building a real models, because here the model was quite simple. It has no dendrites, no axon, no, only two ion channels. And so in addition to talking about more details of how to build a realistic biological model, I will also talk about some of the caveats of model building. So in the first part, I made the implicit assumption that the goal of model building was to reproduce in simulation a model, a single model that matches a single real biological neuron. So I had one set of IFIS data coming from one cell, and I wanted to build one model that perfectly match this experimental cell. And thus, but to do so, of course, we will need to have both the morphology reconstruction for this experimental cell and the recording for this experimental cell. But however, when you look at data that is available in the literature, that's almost never the case. So you never get both the morphology reconstruction and the IFIS data for the same neuron, simply because the protocol needed to perform both of these experiments are not often compatible, as they are both destructive. So secondly, in our brain, every individual neuron varies in behavior from the norm, but from a norm established in its population type. So let's say we take an L5PC cell. The morphology and IFIS data coming from one cell is not representative of all the cells in the brain, but it's representative of one type of cell that are the L5PC cell. So with these 2 points, we can see that there is something going on. So sometimes it is better to build a model using data coming from many cells from the same population. So we could have IFIS data coming from many L5PC cells. And by combining them, we could still create only one model, but that is a meaningful representation of the cell population. So then instead of building one model per biological data set, every biological data set for one neuron, we could build one model for many biological data that sort of concatenate this data that reduce it to one useful model. But if we want to do so, the question becomes, how do we combine data coming from different cells in a meaningful way? So let me maybe go into detail about this problem. So let's say we have data from two cells, and we want to compute feature from this experimental data to build a model. So we can say I will aim at reproducing the action potential amplitude and the spiking frequency that I see in my population. So here you can see that I have, for example, the AP amplitude versus the step amplitude for cell one. Oops, I wrote cell one, cell one, and cell two. And the mean frequency and the step amplitude for, again, cell two and cell one. So if I say I want to create a model that uses a stimulus that has an amplitude of 0.15 nanoamps, I can look along this line and check in my experimental data what's the AP amplitude for my cells and what's the mean frequency for my cells. The issue with this is that, as you can see from this line, I do not explore the same regime of the cells, as the two cells have different rheobases. So the rheobase is the current at which the cell starts spiking. So we can see that for cell 1, if I take a target at 0.15 nanoamps, I'm really close to the rheobase of the cell. While if I do the same for cell 2, I'm already in a regime where the cell is spiking quite intensely. And so there is an issue. It means probably that our experimental cells were of different size, and thus they have different input resistance. And so when we take a target defined as an absolute current, it means we will average, for example, let's say we average these two features to create a target for a model. We will average along for the two cells at different regime, and so it will be meaningless. So we need a better method than that. And so what I propose in what is done in BluePy as a solution for this problem is that first, maybe we can rescale the amplitude of all the experimental recordings by the rheobase for the cell. So I would take if I have a step current, I will first find the rheobase for the cell, and then I will divide the amplitude of the step current by the rheobase for the cell, and thus we'll have the step amplitude expressed as a percentage of the rheobase for the cell. And as you can see here, in our case, it would be like putting the rheobase for the two cells at the same point. And then once we do that, if we take a target expressed in percentage of the rheobase of the cell to revert that as an absolute current amplitude, then we can probe along this line, so along this amplitude, the same regime for all of the cells. And then it becomes meaningful to do an average of the properties along this target. So the issue is that to do that, we need to find the rheobase of the cell, and we need to do this operation of dividing all the amplitude by this rheobase, and then express the target as a percentage instead of as an absolute current. The good thing with that is that now we can compute. So earlier we were defining the score as the absolute difference between the experimental feature and the model feature. And now we can switch to defining the score as the difference between the mean experimental feature and the model's feature. But we can even go further than that, is that since we know we now have a mean for the feature at a given amplitude, we also have the standard deviation across our cell population. And we can use this standard deviation. We can say if there is a lot of variability for one feature in the biological cell population, then it means that our model does not need to be as precise when aiming for these specific features. So what we can do is that we can weight the score for a specific feature using this standard deviation. This way, a standard deviation that's higher will decrease the score, and the standard deviation that's lower will increase the score. So let's say we have a population of L5PC cell, and they all spike exactly at the same spiking frequency. Then the standard deviation will be very small. And that will be important for our model to capture this property and fire also exactly at the same spiking frequency. In the other hand, if in our cell population, we see that all of the cells spike at different AP amplitude, then we'll have a high standard deviation for AP amplitude. And thus, for our model, it won't be very important if the model spikes exactly at the mean AP amplitude we saw in our cell population. So that's a new way to define the scores that may be more meaningful than what we're using in our simple model case. A second point of detail that's quite important is that before, in our simple model case, we saw only step currents. So it was simply a step with an onset and offset, and it was a straight step. There was nothing going on. But one interesting thing is that if you have the matching electrophysiological recordings, you can actually use other types of protocol. You can use REMs, you can use sine waves, you can use noise input, and so on. And to match these different protocols, you can define many. Like you can try to create new features, even, or look at the one over Eiffel and try to characterize different aspects of your neuron. So that's quite important if you want to get some specific thing right, such as the time constant of the membrane and so on. And the second thing is that for a given protocol type, so let's say a step, you can also use different amplitude of the same stimulus to constrain your model. So let's say you want to fit the current versus spiking frequency of your model, where you can take several data points along this line, so several step amplitude, and compute the mean frequency for all of these amplitudes, and try to fit, therefore, your model with several amplitudes and several protocols. So just about protocols, just to remind that a caveat is that step recordings are not something that happens in the brain, so not biologically realistic input. In our brain, the neurons are not subject to step currents. And so even though we use them and we try to build model using this step current, it's important to remember that it's not biologically realistic. So even if our model performs well in this setting with step current, it might not in a real circuit. Okay. The second detail I wanted to come back to is about mechanisms. So earlier we used the mod file, the SKV 3.1 and the NHEG mod files. I just wanted to say that you can code mod files for anything. So like it's over, you can have mod files for the calcium dynamic. You can have mod files for many ionic dynamic, diffusion and so on. And same caveat as for protocols, mechanisms mod files are phenomenological models. So our sodium mod file is not a direct modeling of the channels as they are present in the brain. We are doing here a molecular dynamic simulation of the opening and closing of the channel. It's a phenomenological model. And the only thing that governs our model is its equation and the maximum conductance we are trying to fit using the optimizer. So that's something to remember. And also an interesting thing we can do with mechanisms is that you can also create stochastic models. So today, all the mod files we use are deterministic, but you can also have mod files that draw number out of a random number generator. And with that, you can have a sort of noise in your base voltage or in your spike, and you can create irregular or stuttering cells. So that can be useful if that's what you are looking for as well. But just be careful with stochastic models because they are extremely computationally expensive. By default, Neuron uses a trick to speed up the computation, called a technique called CVOD, where it decreases the sampling rate when there is little change in the voltage, but increases the sampling rate, for example, around APs when there is a lot of change in the voltage. But if you use a stochastic model, then Neuron will be forced to draw numbers from the random number generation at each time point. And thus you cannot use this CVOD technique anymore, so it can increase the computational cost by 10 almost sometimes. And finally, the last thing about mechanisms, as you saw in the notebook for the simple models, we had to choose bounds for the parameter. So I chose like bounds at random a bit. There was this CM that was between, I think, 1 and 20 or something. And then same for the NHEG and SKV 3.1. We had this maximum conductance that was going from 0.1 to 20 as well, something like that. It can be very tricky to find correct bounds for the parameter as the models are phenomenological. So the conductance might not mean the same thing as what you see in papers where they measure the conductance. So sometimes it's a bit of iterative process to find the good bounds for the optimization. And the last point on the bounds is that choosing the bounds can also be remember that can be restrictive for the optimizer. Let's say here you choose these bounds. So here the grid square marks the upper and the lower bounds. If the bounds are set too narrow, then your optimizer won't be able to reach the best solution. So the best model you could have for your the best set of parameters you could have for your model. But if the bounds are too large, it is also unlikely that the optimizer will find the best solution as well. So here you can imagine that if we had bounds that are 10 times the size of this -5 to 4 graph, then it will be unlikely for the optimizer to arrive in this specific fitness well and to obtain the best model. Therefore, it takes some time to learn what bounds to choose. You can get inspiration from experimental data, of course, but it doesn't always match. So it's a bit of a mix of intuition and dark magic sometimes. Another details that we can talk about is non-somatic parameters. So in the simple cell example, we only put parameters at the soma and mechanism at the soma. That won't be the case in the example we will look at after that. But there is another question that comes into play, which is that we saw that we got IFIS data from whole cell patch clamp experiments that are performed at the soma. And so the question is, how do you constrain parameters that are in the dendrite or the axon when you only have data about what's going on in the soma? And unfortunately, there is not an easy answer to this question. So because when you inject current at the soma, you only explore through the response the local environment. So the soma may be the start of the dendrite, the start of the axon, the start of the AIS if the AIS is the one generated the action potential. But you still don't have any information about what's going on in the dendrite, and that is very tricky to constrain the parameter at the dendrite. One way to fix that is to use data from the literature. For example, if you know that in L5PC there is backpropagating action potential or calcium spike, or if you know the action potential speed in the action, the attenuation of the EPSP in the dendrite, and so on, you can also use this kind of data or pair recordings or even local field potential data and try to design in the simulator a protocol that will target this specific feature. But often it is not a trivial problem. And same as for the soma, sometimes it can be also quite complicated to know which channel to put where in the dendrite, in the axon, and so on. Because if you have transcriptomic data tells you what is in your neuron as an entity, but not what specifically in the soma, in the axon, in the dendrites. One last point, maybe one of the last point about choosing a final model. So during optimization, as we optimize over our population, so a set of solutions, we end up with actually several solutions. In the simple cell example, we chose the first element of the Hall of Fame, but we could have chosen the second one or the third one if they're also good solution. And so once you arrive at the end of your optimization, you have many good solutions. The question can be which one to choose. And the problem will get worse as you will add more channel to the model. You will have more local minima in your fitness landscape, more sets of parameters that show appropriate behavior. And so you have need to know how to choose which one is the best out of all of these models. And here, my philosophy is a bit to follow what Jean-Marc Goya says in his paper, is that the region of parameter space corresponding to a phenotype are larger than the regions defined by the covariation of ion channels, allowing substantial variability without disruption of the target phenotype. And when he says that, you could think that he talks about models, so that he said that indeed, when you're building models, you can build several sets of solutions that give rise to the same phenotype. But here in his paper, he's actually speaking about biological neurons. And what he's trying to point out is that in the human brain, there is also variability in parameters, in channel densities, in channel expression, and so on. That is sometimes quite large. And so it's okay to have several set of parameters that are degenerate, that lead to the same solution, because the brain does the same thing as well. So it's a bit of like bird can fly, bat can fly, plane can fly, but they all fly through different means. So there is a bit of that. Okay, so that was all what I wanted to say for this second part. Now we will switch back to the notebook. So we have two choices here. Let's go back to our notebook. And this time we will go to the tutorial 2. And here we have two choices. We have a bulk extraction notebook where I can demonstrate how to extract and compile electrical feature from many different experimental cells. So this one I will need to do a bit of coding because I wanted to demo more live how I think about these kind of things. And then there is a second notebook that is actually an example I took from BluePyopt, and that demonstrate how to build an IL5 PC cell that has many mechanisms and that try to fit a set of target that is already defined. So I think what I can do is that I can go through this example first, this L5PC example, and then if we still have time, I will go through maybe during the next session on the bulk extraction, if there are still people who are interested in that. So I hope you are already, you still have your lab open and you can access this Jupyter notebook. Let me know if it's not the case. Okay, let's close a bit. I think we had open. Okay, good. So let's go back to model building. So here our goal, make that smaller. Sorry, the video is in the way. So here now we are going to create a bit more of a complex model. It will be a layer 5 pyramidal cell, a neocortical layer 5 pyramidal cell. And I won't demonstrate how we obtain the targets or the feature for these cells, but we'll go over them in the first time. So we arrive in this directory. In this directory, we have our notebook, and we also have scripts that are used to instantiate the model. So this script contains everything I showed explicitly in the simple cell case. I showed you how to create the BluePyopt cell model. We have a script that creates the evaluator, so that reads some file I will show you after that define the protocols, the fitness calculator, and that create a cell evaluator. And then we will not go over these ones. Maybe we can delete them because I'm not sure we'll use them, but let's leave them for now. And then we have a checkpoint directory that will contain a checkpoint or optimization. We have a config directory. In this config directory, we have a JSON file containing our features, so what we'll aim for. So in this feature, we are going to aim for some back propagating action potential property. So the AP width, height, spike count, what's something happening at the downwrite, so the amplitude from voltage base. And then we will define 3 steps of different amplitude. And for the 3 steps, we will have a set of E features, AP height, HP slow time. So we can look in the documentation of EFL to look exactly at what these features are doing. And we'll repeat it 3 times, so for 3 different amplitudes. We have a second file that defines the mechanisms we want for our model. So here our model will contain for the basal downwrite the AH channel. For all, we have a passive channel. On the apical, we have AH, IM, SKB 3.1, NAT channel. Axonal, we have a good set as well with a calcium dynamic, potassium dynamic, and sodium dynamic, and same for the soma plus AH. Then we have also a file to define the parameters of all of these channels. So same as what I showed in the notebook, for the simple models. So all of the parameters are defined by their name, their location, and a value that can be either a fixed parameter or a bounds if it's a parameter we want to tune. So you can look in this more in detail after the tutorial. And finally, we need to define the protocols. So to define these 3 steps plus the back propagating action potential we are going to try to optimize for. So we see that the steps are still defined by a delay, an amplitude, duration, dot duration. So both for the holding and the step itself. You can see that the holding is a negative amplitude, and then we add on top of that a positive amplitude that is the step. Okay, so we have basically everything we had before, but it's simply more numerous. So now we can go back to our notebook. So let's compile. Doesn't like my. Oops, I don't have the right. Oh yeah. So if you have this issue, of command not found for neuron IV mold, it means you don't have neuron installed. And this happens if you don't select the right kernel, because by default on Collabs, if you use the Python 3 IPy kernel, you don't have neuron or anything. So here we just select the experimental release. Okay, and I will also maybe add, I'm not sure bluebrain is installed on this one. Oh, it's okay. We get a warning. Okay, error. That's not good. Still work though. I think that might have been the error you got. Not sure what's going wrong. But anyway, if it compiles, it compiles. Okay. So then, similarly to what we had for the simple model, we can instantiate our morphology. So here, our morphology is way more detailed than the one, some permission denied. Do you have the folder called x8664? As long as you have this folder, it was created properly. It means you have the. Okay, so it's perfect. It's okay. Then you can use the one I compiled yesterday.
Yes.
Perfect. Okay. You won't. I think you have this issue because maybe on the collab I need to give access, permission to change, to modify things, or maybe something like that. But I'm not so familiar with collab for now.
Yeah, that's exactly what happened.
Okay, perfect.
To me before, but it creates the folder.
Okay, perfect. So we're going to load the morphology as we did for the simple cell. And same as before, I need to matplotlib inline. Oops, not here. So to plot the morphology. Okay, so as you can see, our morphology is way more detailed than what we had for the simple cell. So here I think it's a rat L5PC morphology, if I remember correctly. And based on this morphology, we can create bluebrain morphology. It's okay, it's instantiated. Then we will add our parameter that we'll read from our config file. You can print the name of the parameter. So same, we have many more. For the calcium dynamic, the potassium, and the sodium. And then we'll import one of the functions for this script, the L5PC model that contains this function defined parameters. And this will automatically create a parameter object from all of these config files. So we can see that we get all our parameters. Okay, everything looks good. We still have some frozen parameter and some tunable parameter for the different sections, axonal, apical, somatic. And then we can define our mechanism still from the same script. Okay, everything seems to be working well. And finally, with these morphology, mechanisms, and parameter, we can create a cell as we did in the simple cell example. Okay, we get morphology, mechanisms, parameters. Everything looks fine. Okay, so I'll just make a list with the names of the parameter that will come in handy to create dictionaries later on. And we're going now to instantiate the protocol. Okay, so the configuration of the protocol that's worked properly. And then we can use this second script, the L5PC evaluator, that contains functions that are used to create the protocol object from this configuration file. And so we define a backpropagating action potential stimuli, 3-step stimuli for the soma. Okay, all good. And then we're going to define the targets, so the features, so we can read the file properly. Okay. And here we already have defined. So here we can see that it's we have a set of 2 elements. So the first one will be the mean, and the second one will be the standard deviation. Because as I explained, we'll use the standard deviation to rescale the score for every target. And if we use the script L5PC evaluator, we can define directly the fitness calculator. So we see that we have all of our objectives with their mean, the standard deviation. Okay, all good. We define the simulator, so the neuron simulator. All not sure what happened here. I think there is a mismatch between the version of neuron used in this experimental release and the version of neuron. Maybe I will switch. I will do something. I will. How can I do that? What I will do is that I will switch my neuron version, delete all of this, delete this, change the kernel. Okay, that should be fine. The issue is that when the neuron version changes, it doesn't accept the compiled file that we had compiled before that. So I will just update, take an older release maybe. I hope it's neuron 8 at least. And we'll recompile the mechanisms. Okay. Hope they're all there. Yeah, okay, it's good. And now we'll use the same neuron version to instantiate the simulator. Let's go back to where we were. Okay, now it's working well. Okay, so we have our simulator, so we can create our evaluator from our cell model, our parameters, fitness protocol, fitness calculator, simulator, everything. Perfect. Can we print it to check? Everything should be fine. Mechanisms, params. Okay, everything is there. And so, yeah, now we have this evaluator, we can use it to evaluate our model. So here I will take, these are some parameters that were published in one of the papers of bluebrain project in 2015. So they're already optimized. It's already optimized set of parameters. So with this parameter, we should have a really good model already. So let's try it. It's going to take some time to compute because now we don't have a simple cell made only of soma. But now we also have to compute, so to compute the simulator had to compute the cable equation for every single section of the downright and the axon and so on. So it might take longer. And we also now have several step protocol instead of single one. And we get our responses. So, okay, we have 3 steps of increasing current amplitude, and we can see that the cell spikes at a higher and higher frequency as we increase the step amplitude, so that's good. And here we check some backpropagating action potential property at 2 points along the downrights and at the soma. And this is what I can tell you that this is what we are supposed to obtain. And so then if we want to, so this is if we start from, of course, a set of parameters that we already optimized, but us what we prefer to do is optimize our own model. So here we'll do something actually quite quickly because as you saw, the evaluation is a bit long. So we'll only run an optimizer for 2 generations and 2 individuals. And here we will do so using not the CMA optimizer, but the IBA optimizer. So the other one, the first one I presented, that's evolutionary strategy that's more closely related to real biological evolution. So it will take some time to run. Just wanted to check what's the... Yeah, maybe a point that's interesting in the parameters. I talked earlier about scalars for the parameters. We can see in this model that in the apical and basal downright for the IH channel, so the HCN channels, we have a distribution. So we have a formula that specifies how this the conductance for this parameter will evolve as you get further away from the soma. So it's just to show that this is something you can do. Here we have an exponential increase, I think, with the distance. Yes, that's correct. And this distribution must be defined somewhere. Oh, just here. Okay, so it's good. And that's also a parameter you can tune, which is the, if let's say you wanted to parameterize this distribution, you could also here have a parameter. So have like a distribution parameter, and then define a new parameter here to optimize also the parameter of this distribution. So there is lots of things you can do with that. Alors, the optimization is finished. So it runs for 2 generations for 2 offspring, so 4 evaluation. Can print the best individual in the Hall of Fame. So it's just a set parameters. Okay, so we get something. We have values for all our parameters, the calcium dynamic, and so on. And let's plot the response for this set, for this best parameter. Okay, so this is what we got. So as you can see, it's not good at all. So we get our 3 steps that don't really spike, and we don't even have the backpropagating action potential dynamic. And that, of course, is the case because we simply run our optimizer for 2 generations for 2 individuals, so it's extremely small. But if we had run that for many more generations, we would little by little convert from this kind of solution to this kind of solution, which is what we want to obtain in the end. So to conclude this tutorial, I just want to go to 2 things. The first one is in case. So as you could see here, we optimize always our model through BluePyOpt. And at the end of optimization, we still have a BluePyOpt object. So that's all we have. We don't have a neuron simulator object. We have a BluePyOpt object. And the question can be, once I have this set of parameters, how do I export my model and what can I do with it? Most of the time when people share their model in the neuron simulator, they use a HOC file. And it turns out that BluePyOpt has a function to export models to HOC files. So if we go to BluePyOpt, hope GitHub is online. BluePyOpt is model is in HOC, create HOC, pretty close. Alors, oops, create HOC. Okay, so there is a function called create HOC. So we could take this. Our evaluator is called evaluator. So evaluator.cell model .x create HOC. Our parameter values is our best parameters we got from our optimization. We're going to use this Ginger template to create the HOC file. We simply use template of what the HOC file is supposed to look like. And if we run this cell, perfect, we got some string that represents the model as a HOC file. And then we simply have to, not sure if it does it automatically. No, it does not register this as a file. So if we were to put this string in your HOC file, then we'll have a HOC file that you can execute when you run, for example, the neuron GUI. Of course, you will still need to provide the morphology, but it should already be, actually, the path should be indicated by default, load morphology, and we have the name of our morphology. So it should run fine in neuron, without, of course, BluePyOpt. And finally, the second thing I want to talk about is the compute needs for optimization. So right now we run already for 2 generations, 2 individual, and it took maybe 2 minutes. If you want to perform a real optimization with this optimizer, you might need around an offspring size of around 100 or 150 or 200, and you might want to run it for 100 generations. So that's around 10,000 evaluation. If you count, let's say 1 minute per evaluation, that's 10,000 minutes. It's already quite a heavy compute on a logbook. And so you might need to set up some kind of parallelization. I would have liked to have time to show how to do that, but I didn't have time to set up on, for example, a Slurm cluster. But if you want to see how you can do that using, for example, IPyParallel, the same example I present here on L5PC is also present in the GitHub of BluePyOpt. So you go to example, L5PC. In benchmark, there are some scripts that show how to create an IPyParallel engine and an IPyParallel controller. In this one, yes. And how to define a map function for, let's say, Slurm, and how that can be used to spread the compute needed for all the individual. So let's say that at each generation, you can spread the compute of every individual on different nodes of your machine. So if you want to learn how to do that, you can have a look at this example. And I think there is in L5PC, there is a function that shows how to create a map function here. Yes, this one, by getting back your IPyParallel controller in Python and passing it to BluePyOpt. So that can be very useful. So that's it for the tutorial about L5PC cell. Now, and so for this last tutorial, I will talk about bulk extraction of features from many electrophysiological traces. And we'll see in practice how BluePyFE concatenates electrical features coming with from many different experimental cells, with the goal of creating a feature vector we can use for optimization. So we won't put it into action, so we won't transform this feature vector into a model, but at least you will see how we can get from FE's traces to the config file that we saw in the L5PC example that looks something like this. So a list of features for given protocols. And also, while during the break, I tried to run an optimization for a larger number of generation, but we can see that we're still not there yet. So maybe I can even run a new one. Let's put more springs, more max10 and run again. And maybe we'll see in half an hour if we got somewhere. But these processes are quite long. In-house, we often run them for 24 hours on many cores. So it's normal that it takes time. Okay, so what we will do in this notebook is doing the same thing we did on the simple model when we extracted features from a single FE trace, but for many FE traces. And to do that, we won't use BluePyFE to instantiate directly our self-cell objects and recording objects. Here we will have BluePyFE doing it for us. So first we will define two config dictionaries. The first one will be a dictionary that will contain the metadata for all the files we want for which we want to extract features. And the second one will be a list of the targets we want to extract for this file. Then we will define the protocols we want to use to compute the Rio base, because as I explained on the slides, we will need to find a way to normalize the amplitude of the traces such that we can average features across cells that have different size and different input resistance. And finally, we will run the extraction and look at the results. So first, to do that, as you can see, I did not code the things yet, so we'll have to fill this thing and so on. And to do that, we will first need to have a look at the IFES data we have available. So the IFES data is present in the IFES directory. So we have 4 cells, and for all of these cells, we have recordings. These recordings all are in two files. We have one with channel 0, that's probably the current, and one with channel 1, that is probably the voltage. And then this file have a name that is the name of the protocol that is contained into the file. Here we have AP waveform, we have ID rest, we have ID thresh, which probably stands for threshold, So to compute the real base of the cell, and IRS we will ignore. And we have an IV, so current voltage. Usually IV protocols are step protocols that contain a hyperpolarizing step that can be used to compute, for example, the resistance of the cell or some hyperpolarized properties. Okay, so we have approximately 4 different kind of protocols for this cell. And if I remember well, we have the same for this cell, AP waveform, AD res, AD thresh, AV. Okay, so it should be the case for all of these cells. So the first thing we'll do is create this dictionary, so this file metadata that's supposed to point to all of these traces such that we can open them. So we will do for file path in glob.glob. Oops. And we will point to ifs. Here we have the name of the cell, and then there are IBWs. So this will iterate over all of our file. We will get the cell name, which is the name of the directory. So we do pathlib dot path file path dot parent. Let's write that print cell name. Oops, need to import my quite a few files. That was not up. Recursive equal true to go in the file in the folders themselves, and it's still not correct. I need to go one layer above. Okay. Let's do maybe I don't remember the command, so we'll do split to get the name of the cell. Oops. Sorry about that. Up. Okay, so here it was just to get a cell name. Then to do the file metadata, each need to contain the same metadata we had in our simple cell. So it was, you can get it at the start of this notebook. Not all. Up. So we need to build this dictionary for every one of our files. So we can do file metadata dot up. File metadata is with singular. So, alors, the current file, the one that contains the ch0 in the name. So we say if ch0 in file path, if ch0 not in file path, we're going to ignore the file. So we ignore all the voltage file for now. Oops, continue. And here we'll put the file path, and here the file path, but we'll change ch0 by ch1. Replace ch0 with ch1. Okay. And I'm going to leave the sampling rate, I'm not sure, so I will ignore it for now, we'll see later. Okay, and I wrote here that the file's metadata format needs to be of the form cell ID, protocol name. Okay. So it means we need to get the protocol name out of the file path. So we have two ways to do that. Either we can, oh, maybe it's okay. So it's quite easy. So we can say file path dot split. Let's take the stem of the file path. Okay, stem dot split. Let's split with the underscore and take the second member. Oops, the second member. So that will give us the protocol name. And we'll define the targets later, but we'll say if protocol, we're going to create all these interesting protocols. And let's say the one we want are for now oops, AP waveform, which is a step actually of quite high amplitude. We have ID rest, ID fresh, ID fresh, and IV. These are the 4 protocols we want to use. So if protocol name in interesting protocol, and let's do it not in. Continue. Up, so we can put this there. If cell name not in path metadata, cell name, this is just for formatting, to have the right format expected by BluePy fee. And then files metadata cell name, append file metadata. So all of this is just to create the dictionary for all the files metadata. And if we do print, preprint, let's see if it works. Oops, I should remove this print. Alors, hop, bprint.bprint. Did I import? Okay, good. So now we have a giant dictionary that contains the configuration toward all of our file. So as you could see here, I could get the name of the protocol from the file name itself. So, but this format, as the question that was asked earlier remind us, is that this format will depend on who is providing you the data. Maybe you will generate your own data, in which case you will know which protocol is in which file. But if someone provides the data to you, then you might need to ask them, for example, a CSV file that contains the mapping between the file name and the path to the name of the protocol and so on. But here it was in the name, so it was quite easy to guess. I just want to add that these names, the name of the protocol, AP waveform, ID rest, ID fresh, and IV, are all names we use at the bluebrain project to define a step protocol. So all of these are step protocols. AP waveform is a step protocol that has quite a high amplitude. ID rest is a step protocol that's a bit longer that we use to look at the firing pattern of the cell. ID fresh is only used to compute the real base of the cell, and AV, as I said earlier, is to look at some passive property of the cell, or to look at some property of the cell during a hyperpolarizing step, such as, for example, SAG, to see the IH channel, or time constant. Okay, so we have our giant configuration file for to read all the files, so that's good. Okay, let's remove it, so it's too long to print. So this is the first of the 2 elements we need to perform the extraction. And the second one is to define the targets, so the features we want to extract from this data. So this is the format it has to follow to work with BluePy. So here we can do it by hand, maybe. So let's say, as I told you, that the ID rest is for firing pattern. Then we can create a new target for our extraction optimization. We'll say feature. Usually when we talk about firing pattern, we want to know, for example, the spike count. So that's a feature that exists in EFL. The protocol will be ID rest. We want it for an amplitude, for a given amplitude, and here the amplitude will be expressed as a percentage of the Rio base. So it means that 100% means the moment the cell spike only once. So of course here we don't want the spike count for when the cell spikes only once. We want like a real firing pattern with a spike train and so on. So maybe we can put 150. So it will mean that we want the spike count for a step amplitude that's at 150% of the Rio base. Then we have the tolerance. So if we ask for an amplitude of 150, it means the software will want us to will look at all the recordings for this cell and will only select the ones that are exactly at 150. So we don't want that because, of course, no recordings will be exactly at 150% of the real base. So we're going to give it a tolerance to look around this 150. So here a tolerance of 20 will be 130 to 170. And finally, we can pass it some settings for IFL. We can say, for example, we want that the threshold of detection of the spikes is at minus 20 millivolt. So these settings are, sure, it feels like I'm getting them out of thin air, but actually defined in IFL documentation. And we can also define other settings, such as when do we want our feature to start being computing and when we want the computation to stop, because we might want the spike count for a specific portion of the signal. But here we're going to leave it like this. Then I'm going to copy this and change the feature. Let's say we want also the ISI CV as early, like we did earlier. We might want the AHP depth. And we might want, what did we use earlier? Maybe the AP amplitude. Let's go back to AP1 and AP width, for example. No, maybe if we're talking about, for example, the firing pattern, let's keep with things of the firing pattern, so the mean frequency. And we have other protocols. So we have IV, IP waveform, IRS. So maybe we can also define targets for these other kind of protocols. So maybe let's go to AP waveform. So AP waveform is usually a protocol that has a higher sampling rate. And having a higher sampling rate is nice because it means you have a more detailed spike shape. And thus it's quite good to compute features related to the spike shape. For example, if you compute AP width, it's better to do it on a trace that has many sampling points. So here we can say, and I know they are quite high amplitude, the AP waveform, so we put 250 for the amplitude, tolerance of 20. Okay, it's good. And maybe let's put some features for the IV as well, protocol. So IV. So there are features that are called sag ratio. So sag ratio measured. So when you have maybe you can do the drawing, which I can do that. So if you have a negative step like this, a negative stimuli, and you will see that your current response will look like this. Then it will come back. It will come back up, and then do like this. And usually these voltage bumps, so the fact that the voltage does not stabilize is extremely fast, is due to the IH channel, the HCN channels. And this can be computed through this feature called sag ratio. Okay, and maybe we can put another constant, such as the voltage base, that will compute just the resting voltage of the cell. And we're going to put here for an amplitude of minus 100, let's say. It's a hyperpolarized amplitude. Okay. So now we have defined some features. Okay, so we have a dictionary with the target, a list with the target, and a dictionary with our files metadata. Now we need to define which protocol we want to use to compute the real base for the cell. And here we can use by default ID thresh. Because it was also the one, I know from this dataset, it was the one that is used during the experiments to compute the real base of the cell. Here, I'm going to set some default IFL settings. It's not very important, but it's just going to configure IFL. So we are going to say that this setting called strict steam interval says that we only want to compute the features during the time interval we give for the feature. So we don't want to compute the spike count outside of the step and so on. The general threshold will be minus 30, but it's getting overwritten here by us who said threshold minus 20. And here we have a parameter called interstep. And what happens is that when a trace is sent to ifel will start to reinterpolate the trace first before performing any kind of computation. And this parameter here says that this reinterpolation will be done with a step of 0.025 millisecond. Okay, so we have our ifel settings. And now the first thing we will do, let's create a new cell, is to use this function, this BluePy function called extract with target. And it needs our files metadata, which is actually called also files metadata. It needs our target, which is also called target. It is our protocol base to be defined here, which is ID thresh. I'm not going to specify the function to use to read the data, but here you could pass a custom function, because by default, BluePy knows what's an IBW and has a reader for it. So I can ignore this one. The map function here is used in case you want to parallelize your computation. Here I'm just going to not do that and pass the Python map function. There is a low memory mode, but here we won't use it because I think we have 2 GB of memory, which should be enough. Our ifel settings, and finally here there is a parameter called the reobase strategy, which defines how the reobase will be computed for every cell. Because by default, BluePy defines either reobase, the lowest current amplitude that induces at least a spike. But let's say you have some voltage traces that contain a spurious spike. Let's say, for example, you were not giving any stimulus to your cell and it was spiking in one of your recordings, then it can give you a wrong reobase for the cell, and that's not what we want here. So here I devised some reobase strategies to this kind of issue, and there is one called flush. And flush would like the reobase to be defined as the lowest current amplitude that triggers a spike, followed by another current amplitude that triggers a spike, followed by another current amplitude that also triggers a spike. So we need a flush of several steps of increasing current amplitude. We take the first one, and that will be defined as the reobase. Okay, so he's not happy because I did not import the function. BluePy extract, import, extract with target. And now he's not happy because we probably did something wrong during the configuration. List object has no attribute key. Yes, indeed. So I did not follow the proper formatting for my. Yes. So here, when we created the config for the files metadata, the format was cell ID protocol name, and I just did cell ID and then a list. So we need to do here a dict, and if protocol name not in. Hop. That's why you should not do like me and actually read the doc string and cell name protocol name dot append file metadata. Okay, now we have the good format. Okay, and now in the background is going to read all of these recordings and extract the features for all of them. Okay, so now we get some warning message. You can see that here it says the automatic step detection failed for the recording IV file blah 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 blah. You should specify turn and tier by hand. We will see what that means. So as I said earlier, when it's reading a step protocol, BluePy will automatically try to detect the step and its amplitude. And this automatic detection is based on the detection of the step, the moment there is a change in the stimulus. And this can fail, of course, if there is lots of noise in the trace or if the trace is flat. So it can cause this kind of warning to happen. So while it's reading all of this file, we will prepare the ground for what's to come. So you can see that this function returns us a cell, which is a list of cell objects, and a protocol, which is a list of protocol objects. So we will iterate over the cell. For cell in cells, we will print the name of the cell, cell.name, and cell. recordings, the length of the cell recording. So we'll have the name of the cell and how many recordings we got from every cell. Okay, so we see that we got only 2 actually cells and not 4 like we were expecting. And but the first one has 120 recording and the other one has 105. So the first mystery is why did we get 2 cells and not 4? So maybe you can print here. Print our file metadata, keys. So indeed, when you have 2 cells, okay. So we see that while these 2 cells have a format in IBW, these 2 cells have a format in B-Wave. Actually, it's the same format. So we'll simply add the B-Wave data. Look for the B-Wave data in addition to the IBW data. Okay. Now, still no. Okay. Let's bring the cell name to see what's going on. So we get everything for our first cell, everything for second cell. We get data for our third cell and for our last cell. So I suspect that, so that's working well. Alors, then what's the format? CH0. We have the issue that now we have CH0 and CH3 instead of CH0 and CH1. So if CH0 not in file path, continue. Okay. So maybe we can hack it a bit and say if cell name we're going to copy this and that. V file. This is often the hacky part of model management, is when you have different sources for your data, you always end up with different data format. And finally, let's check that the protocol name is also. And you see that here we have ID rest with a capital R instead of ID rest with a lowercase r, and maybe the case for other protocol as well, ID fresh. So we are going to put lower, and here we are going to write everything in lowercase just to avoid this issue. We still have only 2. So maybe print here. Not in. I think it's an issue with detection of the protocol name. Okay. So it's okay. The issue is that it's a capital CH and not in and CH 0. Not in file path. And here it's C, which is 0, a capital C. Okay. Now we have all of our cells. Let's read them again. It's going to take some time. So maybe here we can set up for the plot of some traces. Let's say for cell in cells. Oh, no such file or directory such as, okay. So now we have some data actually missing files. So we can check XIV. Here we have CH1 instead of CH3 for this data set. Okay. So let's do this. Else if cell name for CH1 else Let's try again. And we keep running every try to plot something for recording in cell.recordings. Let's put math.lib line if recording dot protocol. Let's look at IV protocols. Protocol name equal AV. We can do recording. You interrupted it. Okay, let's keep running that. We can maybe even, if we want, we can filter them by amplitude. So recording dot amp rel, which is the relative amplitude, so the amplitude expressed as a percentage of the real base, if inferior to 0. Let's say to only look at the IV with negative steps. So it's going to take some time. And we can see another error message here, trying to append NaN to feature ISIC for protocol ID res 150. So we can see that for one of the recording, it was impossible to compute the ISICV, so it could not use it, append it to the list. Okay, so we see that we have 4 cells, and that for all the cells, we have between 80 and 120 traces, so that's good. And we can plot the IV recordings. And we see that here already something bad is happening, because we see that our orange line that we expected to be exactly on top of the blue line is not. So BluePyFi failed to detect the step for this protocol. And we can obviously see the reason, that is that there is a lot of noise in this voltage recording, so for the current recording, so it was very hard for the software to figure out where it step. So one thing we can do is to give this value to BluePyFi ourselves. Let's see. So we see that for all the recordings, the step always starts at around 100 and finishes at 1100. So we can give that to the software. We can say if protocol name equal IV as metadata is called T on, the start of the step, is equal to 100, and the T off is equal to 1100. Okay, and we'll extract again with that value given and see what happens. So of course, in this function, the computation of the real base and the rescaling of the protocols by the real base happen automatically. But you can also look at this function extract with target and run things by hand if you want, by copy pasting the methods that are present inside this function. And while we are here, we can also print maybe the real bases of the cell. So let's stop here. A real base the cell. And we can see that something is wrong here. So I was kind of expecting it. So we can see that for our 2 first cells, the real base is correct. So we have 0.24 nanoamps, and this one 0.41 nanoamps, which is perfectly fine. But here we have something nonsensical, a very large number. And the reason why this happened is that when we specify the units here in our files metadata, we specified amps, voltage, and second, but it's probably not the case for all of our recordings. So if we want it to be correct, we would need to define different file metadata for all our cells. So I propose that for now we ignore these cells that have these different units, not to lose too much time on defining new units. And we simply run again. So now we should go back to only having 2 cells. So here I also define the units by hand, but because in this file format that I have right now, the units are not present in the file. But if you have another file format, it might be that this kind of information is present in the header of the file. We still have this one. Okay, I'm going to remove them by hand. Cell is equal to cell in cells. Cell dot name different from. Let's remove it for now. Okay, so we have only the two cells that have the units that are correctly configured. We still have this issue with the T on and T off. Okay, so we can do print IV, print recording T on and recording T off. See what's going on. So it's defined correctly, but the amplitude is not. That's quite interesting. Okay, this one is correct. And if we put recording dot hyper amplitude, remove this for now. Okay, sounds right. ID rest. Oops, remove this line. Okay, this one work all right. I suspect that for the IV, since there is a very small part before the step, it has a hard time computing the hyper amplitude of the step. But it doesn't seem to be an issue for the other protocols. So we see that here all of the steps are detected properly. And so if we compute if we print the features for these recordings, we should get good results. Recording. Oops. Features. We have a value, spike count, size ICV, HP, mean frequency. Okay, so we get our features. So that's good. And now also what we didn't see here is that in the background, for every protocol, so every target we had, so for example, AP waveform 250, ID rest 150, and so on, it concatenated these features across the different cells. And that we can see if we I'm going to go to the next cell, and we're going to plot everything. Oops, I still did not for the function from bluebrain dot extract port, create feature protocol file, and plot. Okay, good. So now that should have written a config file, such as the one we used for optimization. So we see that you obtain a JSON file saved in the directory example, which contains on one side the feature. So we get ID rest for an amplitude of 150%, the spike count, we get the mean value and the standard deviation. We see that this value was computed on a sample size of 8 recordings with these settings and feature name. Okay, we get the same thing for AP waveform 250%. And we see that despite the fact that we ask for ID rest for, I don't remember, for 1 or 2 steps. We had only 1 step and AP waveform. Okay, so we got this one. We saw that we did not get the feature we asked for IV, because as we saw, there was an error in the detection of this step, so it could not compute the feature properly for this protocol. So it will need some debugging here to find out why it didn't work on this specific step. Okay, and on the other side, we got also the protocols. So here it tried, the BluePyIFE also tried to do a mean of the recording of the protocol for all of these recordings. So for ID res 150, we see that it defined the holding current with a delay of 0, an amplitude of, in average, minus 0.1 nanoamp, a duration of 3000. And on top of that, a step current that has an amplitude that's nonsensical because there was this issue of the detection of the with the units for the second cell. So we need to remove it actually. We need to get something that makes more sense. Cell not that, not in, continue. Let's execute this again. And we'll see it once it's finished. And we can also here have plots for all of the features, the recordings. So let's say we take IRS recordings. So we have all the recordings that are ordered by amplitude. So we can see the amplitude expressed both as an absolute amplitude and as a percentage of the real base. And we can also look at how we have mean frequency. Let's say we can plot the mean frequency versus the amplitude and the mean frequency versus the relative amplitude. So this one is versus the amplitude expressed as nanoamps. So we can see that for this cell, there were two repetitions of the same set of stimuli, and on both repetitions, the cell did not have exactly the same behavior. That's okay, since anyway we are going to average. And we can also express it as a relative step amplitude. So here with 100% of the real base to what we have 350%. And it's using this kind of graph that the mean will be done across cells. So let's go back. Not sure if it's finished already. We plotted everything. You can reopen the protocols. Yeah, it seems to be fixed now. So we have a real amplitude here for the step of 0.8 nanoamps. In addition to that, we also have this file here, which contains the holding current and the threshold current for the cells. So we can see that the cells were holding with a different current, and that they spike at a different current amplitude. Okay, well, I think we have seen everything there is to know at first for the use of BluePyIFE. So we can stop here. I'm not sure if you have any question about this tutorial.
Well, first, thank you very much for the whole explanation. It was very detailed, and I really enjoyed it. But could you afterwards post these notebook also, because I've been trying to follow all the new changes, and it's been a little bit difficult.
Sorry. You mean it was a bit fast?
Yeah, and sometimes I was trying to process what was wrong or what was going on,
okay.
Trying to copy and paste everything, but it was kind of hard.
Okay, no problem. So if you want, I can maybe save these notebooks, and the next time you will open the collab, it should have all of the changes anyway.
Okay, thank you very much.
And if that's not the case, and it doesn't, anyway, I will give you here, I'm going to write into the Zoom chat my mail address. This way, if anyone has any issue with this software, you can directly send me an email, and I can help you set up. Voila. So here for this demo, I was trying to do it with data I don't already know, because it's more interesting for you guys to see the exact process that goes through for doing that. But at the same time, it can happen that the data is not exactly what you expect. Are there any other questions about feature extraction?